Now let's talk about our last big theorem, the divergence theorem, which actually, if you talk to Edward and I, we just call this Stokes' theorem, but we also call fundamental theorem of calculus the Stokes' theorem. Don't let Stuart lie to you, they're all the same. And the theorem is, let E be a bounded solid region in R3 with boundary S, where S consists of finitely many piecewise smooth, closed, orientable surfaces, each of which oriented with normals pointing away from E. Remember, this is kind of the abstraction of boundary where we were easily able to say left, but pointing outwards from E. Let F be the vector field, which is C1 on an open region containing E. And then the double integral over S of f dot ds is equal to the triple integral over E divergence of f dv. Let's put this into practice. Let's try an example. Compute the flux of f being zyx across the sphere x squared plus y squared plus z squared equals 7,921, where the sphere is oriented outward. Well, the divergence of f is just equal to 0 plus 1 plus 0. That's really nice. Wonder why we did that. This sphere bounds the ball B, which is x squared plus y squared plus z squared is less than or equal to 7,921 or 89 squared. So by the divergence theorem, we have the double integral s of f dot ds is equal to the triple integral over the ball, right, because S is the boundary of the ball, of the divergence of f dv, which is just 1 dv, which in other words, if we just have this dv, it's equal to the volume of the ball. And we all know the volume of the ball is this formula of 4/3 pi r cubed, and we get 4/3 pi, some big number that no one cares about. And that is simply how you use the divergence theorem, and it makes things pretty nice. Isn't that right? So let's do another example.